Section: Introduction. In this section, we explore the concept of context hijacking in large language models, LLMs. When LLMs are given specific contexts, they can provide misleading answers in tasks like fact retrieval. For instance, if asked about the location of the Eiffel Tower, an LLM might give different answers based on the additional context provided. This phenomenon, termed context hijacking, suggests that LLMs operate similarly to associative memory models, where the context influences the retrieval of information even if the associations formed are not semantically meaningful. To delve deeper into this behavior, we introduce a synthetic task called latent concept association. This task evaluates how well transformers, a key component of LLMs, can recall information based on semantic similarities in a latent space. We find that transformers excel at this task by using self-attention to gather information and the value matrix to serve as associative memory. Additionally, we observe a low rank structure in the embedding space of trained transformers, supporting existing techniques for enhancing LLM performance. Our contributions include demonstrating context hijacking in various LLM models like GPT-2, Llama 2, and Gemma, highlighting the model's vulnerability to context changes. We also propose the latent concept association task to analyze how transformers handle memory recall in a semantic concept space. By studying transformers on this task, we confirm their ability to implement associative memory based on similarities in the latent space. This work aligns with previous research on associative memory models in neuroscience and deep learning, showcasing the importance of understanding how LLMs form associations to improve their performance. Section Summary. In this section, we explore how large language models, LLMs, can be influenced by context in a phenomenon called context hijacking, where varying contexts can easily mislead LLMs in fact retrieval tasks. We demonstrate that LLMs may behave like associative memory models, with tokens in contexts guiding memory retrieval even if the associations formed are not semantically meaningful. By proposing a synthetic task called latent concept association, we investigate how transformers, like the one-layer transformer, handle memory retrieval tasks by using self-attention to gather information and the value matrix as associative memory, showing emergent low-rank structures in the embedding space. Section: Interpreting transformers and LLMs. In this section, we delve into experiments on various LLMs like GPT-2, Gemma, and Llama 2-7b to investigate the impact of context hijacking on manipulating LLM outputs. For instance, when we give the LLMs the context, the Eiffel Tower is in the city of, all models correctly output, Paris. However, we can alter the LLM outputs by adding extra factual information to the context, which wouldn't confuse a human. This manipulation of outputs by modifying the context is termed context hijacking. Each model has different capabilities, as shown in the examples. Notably, the larger model Llama 2-7b is more susceptible to such attacks. The more sophisticated attacks on Llama also work on GPT-2 and Gemma. Even the instruction-tuned version of Gemma can somewhat understand special words like not. Despite this, these LLMs can still be systematically hijacked, as demonstrated. We explore this phenomenon on a large scale using the COUNTERFACT dataset, which contains challenging counterfactual assertions with diverse subjects, relations, and linguistic variations. Each sample in the dataset includes a context prompt with a true target answer and a false target answer. For instance, a prompt like Eiffel Tower can be found in has the true target, Paris, and the false target, Guam. We introduce hijacking schemes and measure their effectiveness using the efficacy score, S, which indicates the proportion of successfully manipulated samples in the dataset. We experiment with two hijacking schemes, one by adding a specific sentence before the context and another by incorporating factually correct sentences based on relation IDs. The experiments reveal that context hijacking alters LLM behavior, causing them to output incorrect tokens without changing the factual context. This suggests that accurate fact recall in LLMs is not always reliant on the context semantics. This leads to the hypothesis of viewing LLMs as associative memory models, where special tokens in contexts provide clues for memory retrieval. To further explore this idea, we create a synthetic memory retrieval task to assess how transformers, the building blocks of LLMs, tackle this task. Section Summary. In this section, we conduct experiments on various LLMs like GPT-2, Gemma, and Llama 2-7b to investigate the impact of context hijacking on manipulating LLM outputs. By altering the context with additional factual information that wouldn't confuse a human, we demonstrate how the output of LLMs can be manipulated, a phenomenon we term context hijacking. These experiments reveal that context hijacking alters LLM behavior, causing them to produce incorrect tokens without changing the factual meaning of the context, highlighting the fragility of fact retrieval in LLMs and suggesting a potential view of LLMs as associative memory models. Section: Problem Setup. In this section, we explore how fact or memory retrieval in large language models, LLMs, can be seen as predicting the next token based on a given context. Previous studies have looked at the relationship between attention and different types of memory, such as auto-associative and hetero-associative memory. Auto-associative memory involves selecting the closest existing memory based on the context, while hetero-associative memory includes remapping outputs to different tokens. The goal in both cases is to find the most relevant pattern within the context when given a query. However, fact retrieval does not always fit neatly into this framework. The challenge lies in the fact that the output token may not directly correspond to any single token in the context but rather a combination of them, measured by latent semantic concepts. For instance, in the context, the capital of France is, the output, Paris, is not directly linked to any single token in the context, but rather to concepts like capital and France. To address this, we introduce a synthetic task called latent concept association, where the output token is closely related to tokens in the context based on similarity measured in a latent space. In this task, tokens similar to the output token are more likely to appear in the context. We define a latent space consisting of binary latent variables representing semantic concepts, each associated with a specific token. The goal of the latent concept association model is to retrieve specific output tokens given partial context information. This is achieved through a latent conditional distribution, where the Hamming distance and a temperature parameter determine the likelihood of generating random latent vectors or informative ones based on the context. The training objective involves minimizing the cross-entropy loss with softmax for the last position in the context. The error rate and accuracy of the latent concept association model are then calculated based on the predicted output tokens. Section Summary. In this section, we explore how fact or memory retrieval in large language models, LLMs, can be framed as a next token prediction task, aiming to predict the following token accurately based on the context provided. While previous studies have delved into the relationship between attention mechanisms and memory retrieval, we introduce a synthetic task called latent concept association, where the output token is retrieved based on latent semantic concepts, showcasing the importance of understanding the underlying associations between tokens in a given context. Section: Transformer Network Architecture. In this section, we will discuss the transformer network architecture. We start by considering a context of 5 tokens and define its one-hot encoding with a vocabulary size of 46. We also introduce a simplified one-layer transformer model without residual connections and normalization, involving key and query matrices, attention head size, softmax operation, value and embedding matrices. We implement weight tying as used in Gemma. Our focus is on predicting the last position for latent concept association, denoted as the hidden representation after attention and the output token logit. Moving on to the theoretical analysis, we explore how a single-layer transformer can address the latent concept association problem. We introduce a hypothetical associative memory model using self-attention for information aggregation and the value matrix for memory retrieval, resembling trained transformers in experiments. We delve into the network components' roles, value matrix, embeddings, and attention mechanism, validating our claims in experiments. In the hypothetical associative memory model, we demonstrate that a simple single-layer transformer can solve the latent concept association problem. We define the embedding for a token and identify tokens with high probabilities to appear in the context. The model utilizes self-attention to summarize context statistics and the value matrix for output token retrieval, effectively addressing the association problem. The construction of the value matrix resembles associative memory models but without explicit input-output pairs. Empirically, this construction aligns closely with trained models, even in noisy scenarios. Regarding the role of the value matrix, we investigate if integrating its functionality into the self-attention module is feasible for solving the association problem. Empirically, setting the value matrix as the identity leads to lower memory recall accuracy, especially with short context lengths. The value matrix aids in correctly classifying tokens by ensuring the latent representation after self-attention aligns with the embedding vectors. The value matrix's remapping effect helps address classification challenges, showcasing its importance in the model. Section Summary. In this section, we theoretically investigate how a single-layer transformer can address the latent concept association problem by utilizing self-attention for information aggregation and the value matrix for memory retrieval. We introduce a hypothetical associative memory model that mirrors trained transformers in experiments and analyze the significance of components like the value matrix, embeddings, and attention mechanism. Our theoretical claims are validated in subsequent experiments. Section: Embedding, Training, and Geometry. In this section, we explore the training of embeddings and their geometry. When our model is overparameterized, meaning the embedding dimension is larger than the number of tokens, we can use Gaussian initialization to approximately create an orthonormal basis for the embeddings. However, in practice, the embedding dimension is usually smaller than the vocabulary size, making it impossible for the embeddings to form such a basis. Our experiments show that in the overparameterized scenario, embeddings can remain fixed at their Gaussian initialization, while in the underparameterized case, training the embeddings is necessary to improve recall accuracy. We investigate the geometry of embeddings in the underparameterized regime and find a connection between the inner product of embeddings for two tokens and the Hamming distance between these tokens. This relationship indicates that trained embeddings naturally capture similarity in the latent space. The structure of these embeddings can lead to low error rates under specific conditions, as detailed in a theorem provided in the appendix. Moreover, the embedding geometry suggests a low-rank structure, especially when certain conditions are met. Even when the embedding matrix is not strictly low-rank, it can exhibit approximate low-rank behavior, as confirmed by empirical evidence. Moving on to the role of attention selection, we acknowledge that attention mechanisms are valuable for highlighting relevant information. By partitioning latent vectors into clusters based on specific criteria, such as the value of the first latent variable, the attention mechanism can focus on tokens within the same cluster, reducing noise and emphasizing important information. Considering context hijacking and memory recall misclassification, we explore how manipulating the context in language models can lead to misclassification. By altering the context to resemble a different conditional distribution, models may misclassify tokens. Longer contexts with diverse samples can increase the error rate, as indicated by theoretical results and empirical observations. Additionally, we discuss reverse context hijacking, where adding sentences containing target words can enhance fact recall rates. Section Summary. In this section, we explore the training of embeddings and their geometry within the context of overparameterization and underparameterization scenarios. We observe that in overparameterization, frozen Gaussian initialized embeddings suffice, while underparameterization requires training for improved recall accuracy. The relationship between inner product of embeddings and Hamming distance reveals that trained embeddings inherently capture similarity in the latent space, leading to low error rates under specific conditions. Additionally, attention mechanisms aid in selecting relevant information by focusing on tokens within the same cluster, mitigating noise and enhancing model performance. Lastly, we delve into context hijacking in large language models, where altering the context to resemble a different conditional distribution can lead to misclassification, highlighting the importance of context diversity in memory recall. Section: Experiments. In this section, we will delve into the experiments conducted to understand the importance of the value matrix, embeddings, and attention mechanism in our model. The value matrix plays a crucial role in maintaining high memory recall rates. We first compare the impact of training versus freezing the value matrix as the identity matrix for different context lengths. Our results show that freezing the value matrix can significantly reduce accuracy, emphasizing the importance of the value matrix. Additionally, we investigate the alignment between the trained value matrix and the constructed one, showing that they are functionally similar. Moving on to embeddings, we explore the necessity of training them in the underparameterized regime. Our experiments demonstrate that training embeddings is essential, especially when the dimension is smaller than the vocabulary size. We also analyze the structures formed by embeddings in trained transformers, revealing interesting relationships between inner product values and Hamming distances. Lastly, we focus on the attention selection mechanism. By studying a specific class of latent concept association models, we observe that the attention mechanism effectively filters out noise and concentrates on relevant information. The experiments further confirm that attention selects tokens within the same clusters, highlighting its role in capturing informative conditional distributions.